Okay, so now we're going to turn our attention to calculating power in three-phase circuits. In these circuits, we really have to make a distinction between power that's delivered by the source and the power that's actually consumed or converted by the load, as they're not going to be the same. This is due to internal losses inside the generator, the source impedance of the generator, and also due to the I squared R losses in the transmission and distribution lines that connect the generator to the load. Additionally, you're going to see that we're going to make a distinction between power per phase and total power. Power per phase is just the power converted by the load or power sourced by an individual phase of the voltage or current source. Total power is just the sum of the three-phase systems. So in this YY connected load, the average real power associated with phase A is going to be, the average real power is going to be the magnitude of VAN, the voltage across this, times the magnitude of the current through it, times the cosine of the voltage angle between the two, right? Power in phase A, average real power. This is the same power formula that we expressed before. It's the magnitude of the voltage VAN, right? We multiply that by the magnitude of the current, which is IAA, and then we take the phase angle difference between those two, and we do the cosine of that, theta VA minus theta IA. And just remember that we're just talking about the cosine of the angle between those two, right? We could have found reactive or apparent power by multiplying VAN times IAA star, to find average reactive power. It's VAN magnitude times IAA magnitude times the sine. These are just the same equations that we've already developed for single-phase circuits. What's interesting is in a balanced system, the magnitude of VAN, the voltage across here, is going to be the same as the magnitude over here. The angles will be different, but the magnitudes are the same. Is the same as the magnitude that's here. Same thing for the current. Current magnitudes are the same, phases are just different. Now we get to the argument of the cosine function. That's the difference between the phase angles, and that's always going to be the same. That cosine is always going to be the same. So magnitude's the same, magnitude's the same, the difference in the phase angle is the same, right? The phase angles will be different, but the difference in them will be the same because they're just shifted by 120 degrees, both of them. And so it doesn't matter if I'm in A, it doesn't matter if I'm in B, it doesn't matter if I'm in C. This formula calculates the power. More generally, therefore, it's written as power in a phase is equal to the magnitude of the phase voltage times the magnitude of the phase current times the cosine of the angle between the phase voltage and the phase current. Total power, that's just in one of these, total power, PT, is just equal to 3 times the power in an individual phase, right? So the total power sourced by this whole thing is the sum of the three, right? So you would just write 3 magnitude of V phase, magnitude of I phase, cosine of the angle between the two of them. We could also, if we wanted to, rewrite this in terms of the line voltages and the line currents. That's somewhat commonly done. Remember, in a Y connected load, the line current is equal to the phase current divided by the phase voltage divided by 3. So we would have to put in V line over radical 3 here, and the line and the phase currents are the same. So power phase is just going to be equal to, we do the radical 3 substitution here, which is V line over radical 3. Take the magnitude of that, and then you got I phase is the same as I line, so that can just be a direct substitution. Cosine is going to be the same here, cosine of theta, and we get that. So power formula for in terms of the magnitudes of the phase voltages and currents, or the magnitudes of the line voltage and current. That there should be an L. Doesn't matter because they're the same, but should be an L. Similar equations can be developed for both reactive power and apparent power, right? So we could write I guess I'll just summarize them all actually on this slide. I got a little bit of space here to do it. So yeah, let's just summarize them here. So we've got power per phase is going to be magnitude of VAN times magnitude of IAA, excuse me, cosine of the angle between the two. That's, we were writing that more generically as magnitude of V phase times the magnitude of I phase, cosine theta. Total power is just 3 times the phase power. And then we were going to make the substitution, power in one phase is equal to the magnitude of the line voltage over the square root of 3 times the magnitude of the line current, since it's the same in the delta connected load, cosine of theta, right? And then we could go ahead and write these for reactive power and apparent power. I guess I will go ahead and do those. So the reactive power, getting tired here, making some mistakes. Reactive power Q per phase is just equal to the magnitude of the phase voltage times the magnitude of the phase current times the sine of the phase angle between the voltage and the current through it. Q total is just equal to 3 Q phase, right? They all sum up in a balanced load. This would equal, if we were to do the math, we would plug this in, we would get, we would put radical V phase over radical 3, and if you multiply 3 times 1 over radical 3, you end up getting radical 3 times V, magnitude of V line, magnitude of I line, still times the sine of theta though. All right, so that's just 2 math steps combined into one. I substituted V line over radical 3 for V phase, and then I multiplied 3 times 1 over radical 3 to get that term radical 3 in the numerator there. S phase is just going to be P phase plus JQ phase. Right? Not too surprising right there. If I want the total apparent power, I just take those two. That can be directly calculated using the complex conjugate calculation that we showed previously. And then we could come up with a total apparent power that's just 3 times S phase. And sometimes you'll see that written as radical 3 VL IL at an angle of theta. I've seen that formula sometimes in books. Interestingly, in a balanced load, regardless of whether it's Y or delta connected, the average power per phase is always equal to the product of the RMS magnitude of the phase voltage, the RMS magnitude of the phase current, and the cosine of the angle between the phase voltage and currents. The expressions for reactive power and complex power also have the same form for both Y and delta connected loads. Therefore, the calculation of power, reactive or complex, is always the same for either load type. So kind of a simple analysis. Before finishing with an example, I'm going to note that in power systems, when statements are delivered regarding power delivered to a three-phase load, the figure quoted is almost exclusively total power, unless for some reason they indicate otherwise. So now we'll do an example of power in balanced three-phase loads. All right. So what we'd like to do now is an example of three-phase power calculations for this balanced circuit. So we're going to take that YY network that we analyzed 2 examples ago,
not the delta network, but the YY network, the original one. And we're going to just calculate it in terms of the power that it's consuming. So we want to look at the average power per phase delivered to the load, the total average power delivered to the load, the average power lost in the transmission line connecting the generator, excuse me, connecting the generator to the load, the total power lost in the line, the total average power lost in the generator, it's due to its internal impedance, the total VARs absorbed by the load, and the total complex power delivered by the source. So let's take a look at that, these calculations. Pull up a pen. So first we're going to look at the average power per phase delivered to the load. That is, the power per phase is just equal to the voltage in a phase times the current in the phase, cosine of theta V minus theta I. Right. In our previous analysis, we determined the V phase, which was the VA to N calculation that we performed, was 115.22 volts at a voltage angle of negative 1.19 degrees. And we determined that the current, which was both the line current and the phase current in that example, was 2.4 amps at an angle of negative 36.87 degrees. So theta is just going to be theta V minus theta I is equal to negative 1.19 minus negative 36.87, and that's going to give me 35.68 degrees. So 35.68 is the phase difference between the voltage and the current in one phase of the load. Any phase, really. If you look at, VA, VBN and IBB, or VCN and ICC, these numbers will be different. They'll be rotated by 120 relative to the numbers I've given here. But because it's a subtraction inside the argument of the cosine, it's always going to come out to 35.68. So now all I have to do is multiply the magnitude of the voltage times the magnitude of the current and take the cosine of 35.68 degrees. So that's 115.22 times 2.4 times the cosine of 35.68 degrees. And you get power in a single phase is 224.64 watts. That's for each of the phases, right? So in part B, we were asked to determine the total average power delivered to the load. That's just power total is equal to 3 power per phase, this being power per phase, so equals 3 times 224.64 watts. And that gives us 637.92 watts. So that's the total power consumed or converted by the load, and we mean real or average power here, whatever you want to call it. Part C said, well, tell me what the average power lost in the line is. And remember, the line in this example that we were doing had a resistive element and a inductive element. And the resistive element contributes to the amount of current flow that was drawn, but it doesn't contribute to real power dissipation. Only a resistor can dissipate real power, right? This element, this was 0.8 ohms, by the way, and this is 1.5, J 1.5. The resistor dissipates energy in the form of heat. The inductor actually, remember, will store energy during part of the cycle and release energy during the other part of the AC cycle. And so when we're asked to calculate the power lost in the line, we're only concerned with the resistor. So that's an important analysis. The power lost in the line is going to be the line current times the load resistance. So the line current we just saw was equal to 2.4. Sorry, I squared R. 2.4 amps squared. We multiply that by 0.8. We get 4.608 watts of power radiated by this resistor. There are 3 lines, however, so we need to multiply that number by 3, and that gives us total real power lost in the transmission lines. Which was, let's see. Part D asked us what is the total average power lost in the generator. And remember that the generator had a circuit model that was also a resistor in series with a inductor. In this case it was 0.2 ohms plus J.5 ohms. And we want to know what's the power lost in this portion of the circuit. Well, again, that inductor doesn't convert energy, it just stores and releases. The resistor is the only part that converts any sort of energy. So all we're concerned with here is the I squared R losses associated with that. So P loss in the generator is just, again, that line current squared times R gen. So that's that same 2.4 amps squared. This time it's times 0.2. So we lose 1.152 watts in each phase of the generator. Sum them all up and you get 3.456 watts of total power loss in the 3-phase generator. Just make some space on the slide. Part E asked us to determine the total VARs absorbed by the load. So that's asking us to calculate the reactive power in each phase of the load. Remember the Q in the load, that's just magnitude of the phase voltage times the magnitude of the phase current times the sine of theta. We already performed all this math before, so it's 115.22 times 2.4 times the sine of 35.68. And that gives us Q in the load of 483.84 bars. So that's the total VARs absorbed by the load. Now that's not the total complex power delivered by the source, or the total VARs delivered by the source, because remember we also have the internal impedance of the generator and the impedance of the transmission lines to worry about. So the easiest way to determine total complex power delivered by the source is that we would get S is just equal to 120 and its magnitude times 2.4 at an angle of negative 36.87 degrees, right? That's the complex power delivered by phase A. There are 3 loads, or 3 generator phases though, so we multiply that whole thing by 3, and so you get 3 times 120 angle 0 times 2.4 angle negative 36.87. And you may say, oh, hey, hold on a minute, so this should be complex conjugate, excuse me. You might say, hey, hold on a minute. The angle of the voltage and the angle of the current are different in the different phases. Well, while that's true, remember when we multiply them, we're just adding them together. And so what happens is that we're really concerned with that difference calculation there. And so this ends up being 691.20 plus J 518.40 volt amps of complex power delivered by the generator. You see that the complex power here, 483.84 VARs, is a little bit less than what's here, and what accounts for that is the transmission line and the internal impedance of the generator. So, sorry, I forgot that's I multiplied that by 3 there. 115 times 2.4 times sine of 35.68 times 3 to get the total VARs absorbed by the load, right? Okay, so that ends this lecture series on the physical network and the load devices.